All right, so here's an example where I can show you why linearly independent is an important concept. Okay, so you have y double prime equal to y, and we want to find the general solution. You can check that if you take the e to the x and differentiate twice, you get the same function. If you differentiate e to the negative x, the first derivative is negative e to the negative x, but the second derivative is back to e to the negative x. So these are the two solutions. And we just want to say, oh, C1 of the first one and C2 of the second one is the general solution. But we can't be for sure because maybe there is some linear relation between them, and what we thought was a totally new solution, different from e to the x, was just, what if this was some linear multiple of the first one? Then we have to go and find something totally different. Okay. So here's our worry. We're temporarily anxious about the following fact. Is it true that maybe e to the negative x is just some constant times e to the x? If that's true, is it good or bad?
Bad.
It's bad. That means we have to go and find another solution. Okay. If this is false, if this is never true, is it good or bad? It's good because that means these two are genuinely different, and we now have our two solutions, and this will be the general solution. Okay. That's what we're trying to show. Okay. Now another form of this is equivalent to saying that C1 e to the negative x plus C2 e to the x equal to 0 should imply that C1 and C2 should equal to 0. So these two statements are the same. No, they're actually the statement that this is never true. So there is no C such that this is true. Okay. So let me explain why. If you had C1 and C2 non-zero, and then it satisfied this equation, how can you turn this into this statement? You can just solve for e to the negative x, right? If you solve for e to the negative x, this will turn into what? E to the negative x is equal to negative C2 over C1 e to the x. And you can take C to be this thing. So if there is some non-zero value that will satisfy this, that means there is such a C. If 0, 0 is the only case that this is true, then that would mean that there is no such C, because if there was such C, then you can move it to the other side and take C1 to be 1 and C2 to be negative C. That would be a solution. Okay? So these two are equivalent things. Okay? Now, let's, and actually for proof purposes, this is easier to prove. To show that this implies that, it's easier to prove. Now, let me show you the proof. Proof. If C1 is not equal to 0, then I can repeat this, and you can solve for e to the negative x, and you get negative C2 over C1 e to the x like this. And not only that, I can divide both sides by e to the x. In that case, this is gone, but this will be e to the negative 2x equals to negative C2 over C1. Okay, is there a contradiction? Can this happen? You have a constant function on the right. Okay? What's this? It's a function that depends on x, right?
Yeah.
So, since e to the negative 2x is not a constant function, since e to the negative 2x is not a constant function, this is impossible. Okay. So that forces, that means C1 has to be 0. Okay. Now if C1 is 0, then plug it back into here. So you get 0 times e to the negative x plus C2 times e to the x equal to 0. And then now you can divide both sides by e to the x, right? Then what do you get? You get C2 equal to 0. Just by dividing by e to the x. Because this is gone, 0 times anything is 0, gone. If I divide e to the x, both sides, I force C2 to be 0. So I just proved that if this is true, then C1 and C2 both have to be 0. And therefore, the two functions above are linearly independent. And because they are linearly independent, we can happily say that those are all the solutions we want. It's rather contrived approach because we so much want to avoid having to solve the differential equation. So we're basically trying to justify our guesses that we made. And because we're trying to justify some guesses that we made, that's why it requires such a contrived effort. You have a question?
So it is dependent? The one you...
No, we just solved that these two functions are independent.
I thought if they both equal 0, then it's dependent.
No, if they're both equal to 0, then they're independent. That's what I said over here. If they're all equal to 0, then they're linearly independent. If there is some non-zero ones that would make this true, then they're dependent.
All right, now
Okay.